Hi, I'm Collins Weber, and this is the physics quiz tutorial for extra credit. I chose to do problem 3P36 on page 130. And it says, in June 1997, the nearest spacecraft on its way to photograph the asteroid Eros passed within 1,200 kilometers of asteroid Mathilde at a speed of 10 kilometers per second relative to the asteroid. From photos transmitted by the 805 kilogram spacecraft, Mathilde's size was known to be about 70 kilometers by 50 kilometers by 50 kilometers. The asteroid is presumably made of rock. Rocks on Earth have a density of about 3,000 kilograms per meters cubed. So part A says to make a rough diagram to show qualitatively the effect on the spacecraft of this encounter with Mathilde. Explain your reasoning. So when the spacecraft interacts with Mathilde, there's a force of gravity that is going to point straight towards the asteroid, and this will cause the craft to orbit around the asteroid like this. So that's part A. Part B. Make a very rough estimate of the change in momentum of the spacecraft that would result from encountering Mathilde. Explain how you made your estimate. So you need to start with the momentum principle, where the change in momentum equals the force times the change in time. And the force in this problem is your force of gravity, which is equal to negative g, the mass of the craft, times the mass of the asteroid, over r squared, the distance between the two. And you have to remember that g is negative because the force of gravity is pointing towards the asteroid. To solve for the mass of the asteroid, you need to know that mass is equal to volume times density. And once we know this, we can calculate the mass of the asteroid. So the volume is 70 kilometers by 50 by 50. And you have to multiply this by 1,000 meters cubed to convert your volume from kilometers to meters, and then 3,000 kilograms per meters cubed is the density, and this gives you a mass of 5.25 times 10 to the 17th kilograms. Okay, so now we can calculate for the force of gravity, which is equal to negative g. G is 6.7 times 10 to the negative 11, times the mass of the craft, which is 805 kilograms, times the mass of the asteroid, which we just solved for, and then divide that by r squared, which is the distance between the two, which is given up here as 1,200 kilometers. So once again, we need to convert it to meters by multiplying by 1,000. So that will be 1,200,000 meters squared. So you get a force of gravity that is equal to negative 0.0197 newtons. So now we need to calculate delta t to find the change in momentum. So delta t isn't exactly given. However, part C and part D uses a delta t of 1 day. So that's what I'm going to use for part B. So 1 day, which is equal to 86,400 seconds. Convert to seconds. And then we can solve for our change in momentum. Force of gravity times change in time equals about negative 1,699 kilogram meters second. Okay. Part C. Part C says, using a result from part B, make a rough estimate of how far off course the spacecraft would be 1 day after the encounter. So first we need to calculate the final momentum. So the change in momentum, which we just calculated, is equal to the final momentum minus the initial momentum. And the initial momentum is going to be equal to mass times the initial velocity. The mass is 805 kilograms, which is given, and the initial velocity is also given as 10 kilometers per second. So multiply by 1,000 to convert to meters per second, and you get 10,000. and this equals 8,050,000 kilogram meters per second. Okay, now we can calculate the final momentum by adding the initial and the change together. So you get 8,050,000 minus 1,699 and get your new final momentum. And then using this, calculate the final velocity, which is equal to the final momentum divided by the craft's mass, which is 805. And you get a velocity of 9,998 meters per second. So the craft was moving at a velocity of 10,000 meters per second, but now it's moving only at 9,998 meters per second in the x direction, which means the velocity in the y direction is equal to 2 meters a second. So we need to know this because we're calculating how far off it will be from its course due to the asteroid, and it's going to change in the y direction because of this force of gravity. So we're calculating the distance in the y direction to find how far off it will be from its course. Because without the asteroid, it would be moving in a straight line. So now that we have the velocity in the y, we can calculate its distance by multiplying this by the time, which once again is 1 day, or 86,400 seconds. And this is going to be equal to roughly 173 kilometers. To give you a visual of this, initially the craft is moving at 10 kilometers a second, all in the x direction, but because of the asteroid and this force acting on the craft due to the asteroid, the craft is going to orbit slightly around the asteroid, which changes its course in the y direction, and this distance is going to be your 173 kilometers. So that's our answer for part C. Part D says, from actual observations of location of the spacecraft 1 day after encountering Mathilde, scientists concluded that Mathilde is a loose arrangement of rocks with lots of empty space inside. What was it about the observations that led them to this conclusion? So we're trying to figure out how they know that instead of a dense asteroid, which we initially assumed Mathilde was, it's going to be this loose arrangement of rocks, which sort of looks like this. So this cube is a lot denser than the loose arrangement of rocks. However, both of these have the same exact volume. So if this one is denser, then that would mean that this arrangement has less mass. And if this one has a lower mass, then that will lead to a different force of gravity, so one that is lower. So your force of gravity is decreasing because your mass is decreasing, and a smaller force of gravity acting on the spacecraft results in a smaller distance of how far off course the craft is after 1 day. So if this is lower, if this force acting on the craft is lower, then this distance is going to be shorter than 173. So your answer to the question, the observation to lead them to this conclusion, is that the distance off course will be less than 173 kilometers. And that's how you conclude that Mathilde is a loose arrangement of rocks.